No matter how much we study the universe, one theory has dominated our understanding of its earliest moments: cosmic inflation. This idea posits that in the first fraction of a second after the Big Bang, the universe expanded at an unimaginable speed. But what if this fundamental premise is only half the story? What if the universe we inhabit has a counterpart, a mirror image that moves backward in time? Imagine the cosmos not as a singular event but as a dual reality, two universes born in the same instant, reflections of each other, moving in opposite directions through time. While our universe unfolds with time moving forward, could there be another that moves backward, carrying the reverse imprint of everything we know? This hypothesis challenges the standard model of cosmology, yet its simplicity allows it to answer profound questions that have puzzled scientists for decades. Why is the universe so uniform on the largest scales? Why does time seem to flow in only one direction? Could this mirror reality hold the key to understanding dark matter itself? In this model, the Big Bang is not merely a beginning but a boundary, a cosmic mirror dividing two symmetrical universes. On one side, particles and forces act as we've observed. On the other, they act in precisely the opposite way. While this might sound like science fiction, the foundation for these ideas lies in concepts like CPT symmetry, a fundamental principle in physics. According to CPT symmetry, particles mirror each other through charge, parity, and time. If this theory proves correct, it could explain dark matter, the mysterious substance that constitutes most of the universe's mass. To explore this idea, let's delve deeper into the evidence, the gravitational patterns of galaxies, the fine structure of the cosmic microwave background, and the very nature of time itself. The story begins in the early 1980s when a new theory emerged to address some of the most perplexing questions about the universe. Among these were the horizon problem and the flatness problem, both of which posed serious challenges to our understanding of the cosmos. To grasp the horizon problem, imagine the universe as a balloon. This balloon, now vast, was once unimaginably tiny. Yet, even at its earliest moments, it appeared surprisingly uniform across immense distances. How could regions of the universe separated by billions of light-years display nearly identical properties? According to the laws of physics, they should not have exchanged information or influenced each other in any way. Cosmologists proposed that a phase of rapid expansion, known as inflation, could resolve this paradox. Inflation suggests that within an incredibly brief moment after the Big Bang, the universe expanded exponentially. Regions of space that were once close enough to interact were pushed apart, creating the astonishingly uniform cosmos we observe today. Inflation also addressed the flatness problem, the question of why the universe appears flat rather than curved on the largest scales. According to Einstein's general theory of relativity, the geometry of the universe depends on its density. If the universe's density were precisely right, space would have the flat geometry we observe. By stretching spacetime itself, inflation effectively smoothed out any initial curvature, resulting in a remarkably flat universe. As inflation caused the universe to expand at an exponential rate, it amplified tiny quantum fluctuations into cosmic proportions. These fluctuations, random, minuscule variations in density and energy, spread throughout the universe, creating slight density differences across vast regions. When inflation ended, these variations became the seeds of structure in the universe. Over time, denser regions attracted more matter under gravity, eventually forming galaxies, stars, and galaxy clusters. The cosmic microwave background, CMB, offers a window into the young universe. Emerging about 380,000 years after the Big Bang, the CMB represents the earliest light we can observe. At that time, the universe was a hot, dense plasma where photons were tightly coupled with matter. As the universe expanded and cooled, photons decoupled from matter and began traveling freely through space. The CMB's temperature fluctuations reflect the density variations in the early universe. Some photons appear slightly cooler, while others are warmer, corresponding to regions of different densities. This phenomenon, known as gravitational redshift, reveals the imprints of the young universe's structure. The European Space Agency's Planck satellite, launched in 2009, measured the CMB with unprecedented precision. Its data confirmed that the observed patterns align with predictions from the inflationary model, reinforcing the idea that inflation shaped the universe's large-scale structure. Yet, despite its successes, inflation theory leaves significant questions unanswered. One major issue with inflation theory is the fine-tuning problem. For inflation to occur as observed, the universe's initial conditions must have been set with extraordinary precision. Even a slight deviation could have prevented inflation from achieving the smooth, flat state we observe. This raises profound questions about why the universe was so perfectly tuned at its inception. Could there be a deeper reason for this fine-tuning? Or is inflation only part of the story? Another challenge lies in reconciling inflation with particle physics. A deeper understanding of elementary particles could provide insights into the mechanisms behind inflation. Supersymmetry, or SUSY, is one attempt to extend the standard model of particle physics. SUSY posits that every particle has a corresponding superpartner, a heavier version of itself. If true, supersymmetry could explain the structure of the universe, offer solutions to the dark matter problem, and provide a foundation for inflation. The ATLAS collaboration at CERN's Large Hadron Collider, LHC, is at the forefront of the search for supersymmetric particles. Researchers are investigating particles like charginos and neutralinos, which could hold the key to understanding dark matter. However, despite advanced methods and higher collision energies, no signs of these particles have been observed so far. One challenge is that SUSY particles, if they exist, may be extremely difficult to detect. Their resemblance to known particles complicates the search, requiring sophisticated tools to isolate subtle signals. Researchers employ machine learning algorithms to analyze event probabilities and identify potential SUSY particles. While no significant signals have emerged yet, the third run of the LHC offers hope for new discoveries. For centuries, physicists have sought a unified theory that explains all forces and particles, a theory of everything. This quest began with Albert Einstein, who aimed to unify gravity with other known forces. Decades later, Stephen Hawking pursued this goal, focusing on a revolutionary concept known as M-theory. M-theory posits that the universe is not made of point particles but of incredibly tiny vibrating strings. Each string's vibration corresponds to a fundamental particle. Remarkably, M-theory provides a mathematically consistent description of gravity at quantum scales, avoiding the infinities that plagued earlier models. M-theory also expands our understanding of space and time, proposing a universe with 11 dimensions, 10 spatial and 1 temporal. Some of these dimensions may be compactified, so small that they remain imperceptible in everyday life. These hidden dimensions could influence the fundamental properties of particles and explain why physical laws have the values we observe. M-theory's framework naturally allows for the possibility of multiple universes. These universes could form pairs, symmetrical to each other in higher dimensional space. A mirror universe would be a parallel brane with reversed configurations where fundamental aspects like time might flow in the opposite direction. This concept aligns with CPT symmetry, suggesting that particles and their antiparticles could mirror each other on a cosmological scale. A mirror universe might serve as a backward reflection of our own, with profound implications for understanding dark matter, time, and the origin of the cosmos. As we explore the possibilities of a mirror universe, it's worth considering how different forms of life might exist within such a reality. Silicon-based life, for instance, could thrive in environments vastly different from Earth's. On Saturn's moon Titan, lakes of methane and ethane, coupled with a nitrogen-rich atmosphere, provide conditions that might support silicon-based organisms. Similarly, the dense, acidic clouds of Venus could harbor exotic forms of life. Even exoplanets like 55 Cancri e, with their heavy hydrocarbons, offer tantalizing possibilities for alternative biochemistries. While silicon-carbon compounds like silicon carbide are robust and slow to decompose, the vast timescales of the universe might allow for the gradual emergence of silicon-based life. The cosmos is vast, mysterious, and full of surprises. Whether exploring the idea of a mirror universe, unraveling the secrets of dark matter, or contemplating silicon-based life, each discovery deepens our understanding of existence. As we gaze into the night sky, we are reminded that the universe's greatest mysteries may yet lie ahead, waiting for us to uncover them.